In the previous video, we covered complementary counting. We covered some very interesting examples that offered us a shortcut to casework. The principle of inclusion and exclusion is another shortcut to casework. Basically, it's a counting technique that computes the number of elements that satisfies at least one of several properties, while guaranteeing that elements satisfy that more than one properties don't count. And it'll make more sense once I explain it more. But essentially, the union symbol, A union B, is a union of elements, and intersection, A, it looks like a backwards view, B, but its intersection symbol, is the intersection of elements in two sets. So the principle of inclusion and exclusion for two sets basically states that if we're trying to count something such that event 1 happens and event 2 happens, then we just find the probability of event 1 happening, the probability of event 2 happening, and subtract the probability where they both happen, because that's overcounted twice. If you look here, it looks like a Venn diagram. Basically, this is A1, event 1, this is A2, whatever the second thing is, and this is the intersection. The union, or such that either event happens, is just each event separately, so each circle, and then subtracting the intersection because it's counted twice. And we'll come back to the principle of inclusion and exclusion for three sets. But first, let's look at an example. So many states use a sequence of 3 letters followed by a sequence of 3 digits as their standard license plate pattern. Given that each 3-letter, 3-digit arrangement is equally likely, so there's no weightage or anything, the probability that such a license plate will contain at least one palindrome, it is m over n. And it's saying that a palindrome is something that reads the same left to right. So for example, 363 is a palindrome, or ABA is a palindrome, because they read the same left and right. But in our context, if we have 3 digits or 3 letters, what does a palindrome mean? The second digit doesn't matter. It has to read the same left and right. The second digit is second when you read it left and when you read it right. Basically, what it means is that these digits have to be the same. So the first digit is equal to the third digit. So when you swap them, the third digit becomes the first digit. So for example, 3x, or let's say 363 will stay 363 because the digits are equal. Okay, so how can we use the principle of inclusion and exclusion, also known as pi for short, in this problem? It asks us to find such that at least one of them will be a palindrome. So let's just find the probability that the letter 1 is a palindrome. What's the probability that 3 letters will form a palindrome? Well, let's see how many choices there are for a palindrome. Basically, we have 26 choices for the first letter, and then after that, we have an additional 26 choices for the second letter. Let's say we have, I don't know, A and then C. And now this last letter has to be the same as the first letter, so just times 1. And the total number of cases are 26 times 26 times 26, because 26 choices for each letter. A shortcut to doing this is to see that no matter what the first 2 letters or numbers will fix the third letter or number. So once you decide the first 2 letters and numbers, the third is fixed, versus in the total number of cases, the third is not fixed. So out of every possible third letter or digit, one of them work, so just 1 over 26. But either way, we get that a 1 over 26 chance that the letter 1 will be a palindrome. Now what about the number 1? Well, the number 1, let's say it's like 3 numbers. It's very similar actually. If it's something like 3, 6, then there's 10 times 10 times 1 choice. This one is fixed. 10 choices for these two. And the total is just 10 cubed, because 10 choices for each of the 3 numbers. Or we could also use a similar logic. The first 2 numbers fix the third. So out of all 10 possibilities for the third number, 1 works. Either way, we get 1/10. But remember, we're overcounting. What if both of these are true? We should subtract that, probably, right? Because they're counted in both this 1/26 and the 1/10. So let's see, what's the probability that these are both true? Well, the probability that the letters form a palindrome is 1/26, and the probability the numbers form a palindrome is 1/10. So the probability that they're both palindromes is 1/260. Okay, so now how do we get the final answer? Well, from here, all we do is we do 1/10 plus 1/26 minus 1/260, right? Because we're subtracting the intersection, just like I showed with the Venn diagram earlier. And this is 26/260 plus 10/260 minus 1/260, which is equal to 35/260, which is 7/52, but it asks for n plus n, so the answer is 59. Now, like I mentioned earlier, not always pi is going to be just 2. It can get more complicated. So for example, there's pi principle of inclusion and exclusion for 3 sets, which basically means that to find the probability that 3 are true, let me draw another Venn diagram so it's easier to understand. We look at these 3 sets. So essentially what this means is that we count the number of values that work for A1, and A2, and then A3. And then after that, we must subtract the overlap. So subtract overlap between A1 and A2, which is this term here. Subtract overlap between A1 and A3, and then A2, A3. But notice that this center section here, we counted 3 times in A1, A2, A3, and we subtracted 3 times, but we must count it once. So we add this region back. So this is what it looks like. Essentially, find the number of ways that satisfy each of the conditions, then subtract the number of ways that satisfy 2 of the conditions, and then add back that satisfies 3 of the conditions, or in this case, all of them. Now, generalize. I know this looks like a scary formula, but don't worry, it's not that complicated. Basically, what it's saying is if you have any n events or any n things you're trying to count, just find the number of ways for each of the n events, subtract for 2 of the events happening, so intersection of any 2 events happening simultaneously, then add back for 3 events, then subtract back for 4 events, then add back for 5 events, and so on, however big your problem goes. And this is very powerful. So now we're going to move on to a problem from Amy that uses pi for 3 events instead of just 2 like in the previous problem. So let's take a look here. Call a set product free if there do not exist A, B, and C in S, not necessarily distinct. This is very important. Without this, the problem is completely different. The most important words of the problem. And RAS such that A times B equals C. For example, the empty set and the set 16, 20 are product free, whereas the sets 4, 16 and 2, 8, 16 are not product free. Why? Well, for this first set, we have 4 times 4 equals 16. And it's very important that A, B, and C don't have to be different. So this is okay, because 4 times 4 equals 16. And in the second example, we have 2 times 8 equals 16. So 2, 8, 16 is not allowed. And we're asked to find the number of product-free subsets of the set 1 through 9. So let's first take a look at all of the sets that contain 1. I mean, after all, let's say we have 1. Can we even have 1, first of all? Actually, it turns out no sets are possible with 1. Why? Because 1 times 1 equals 1. And in the problem it says A, B, and C. So and they don't have to be distinct. And 1 does not have to be distinct from the other one. So just the act of having 1 in the set automatically makes it so that any choice of A being 1, B being 1, and C being 1 is allowed, because they don't have to be different. So we literally cannot have 1 no matter what. It doesn't matter what the other elements are. So we can just treat this as a set from 2 to 9, and we're asked to find how many product-free subsets of 2 through 9. And that's the same thing as how many product-free subsets of 1 through 9, because no subsets with 1 work. Okay, next. What other products exist besides the ones that include 1? Because those we don't even care about. Well, there's 2 times 2 equals 4. So we cannot have the group of numbers 2, 2, and 4. Anything else? Well, many actually. 2 times 3 equals 6. And so we can't have the group of numbers 2, 3, and 6. Anything else? Well, 2 times 4 is 8. Well, but let's stop here and see. In this first subset, we don't actually need to have 2 2's, because we can repeat elements to be A and B. So A and B can both be just one of the 2's. So essentially we don't even need the second 2 here. Just 2 and 4 suffices. So that means, what about 2, 4, 8? We're asked to find 2, 4, 8. Is that a valid product? Well, yes it is, but as we'll see later, we won't actually have to worry about it. Okay, what about 2 times 5? That's too big. It's 10, it's outside our range of 9. Okay, next we move on to 3. We already counted 3 times 2, so we'll just start with 3 times 3. 3 times 3 equals 9. And for this product to occur, we had to have a 3, and we don't have to have 2 3's, just 1 will suffice, because they can be duplicated. And we have to have a 9, so this group of numbers 3 and 9 has to be there for this product. 3 times 4, too big. It's 12, and it's outside our range of 9. And we'll notice that anything else, 4 times 4, 4 times 5, because the square of 4 is more than 10, any product of 4 will be more than 10. Same thing for 5. Any product of 5 or more will be too big, and so on. So these are really the only products possible. Okay, so now let's look at what we want to count here. We're asked to count product free. So instead of counting product free, let's do complementary counting and count the ones that contain a product. So that contain 2, 4, or 2, 3, 6, or 2, 4, 8, or 3, 9. But notice a minute, like I mentioned earlier, 2, 4, 8, and 2, 4. If a subset contains 2, 4, then it already doesn't work. So if a subset, for the subset to be product free, it has to not contain 2, 4. And by not containing 2, 4, you don't need to, this 2, 4, 8 is kind of redundant, because by not having 2 and 4, we automatically don't have this subset over here. So what does that mean? That means, well, we don't really care about this, because anything that doesn't contain 2 and 4 already won't contain 2 of the pieces you need for this product to be true. And without both 2 and 4 being there, there's no way for this product 2 times 4 equals 8 to be possible, since you need 2 and 4 plus an additional 8. Okay, so there's no other redundancies, as you can see here, because all of these have their unique numbers. Okay, so now how do we count this? Well, let's first count how many possibilities there are, how many products. Remember, we're doing complementary counting. So how many subsets that contain one product? Okay, let's see. First of all, how many subsets are there that contain 2, 4? Well, notice that, remember, we're just completely excluding 1. We don't even care about that. We're not even doing it in our complementary counting, because there's literally nothing that works with 1. So with 2, 4, how many subsets include 2, 4? Well, 2, 4 are 2 elements out of 8 total elements here. 2 through 9 is 8 elements. So for a subset to contain 2 and 4, those 2 elements has to be there. And there are 6 remaining elements. So number of subsets with 2 and 4 will just be 2 to the 6, because there are 6 elements left besides 2 and 4 that we can choose to have in our subset. And for each of them, 2 choices: in the subset or not in the subset, as we saw in our subset section earlier in the video series. Now, what about 2, 3, 6? The number of subsets with 2, 3, and 6, well, there's 8 total elements in the set, so 5 are left after 2, 3, and 6 are in the subset. So 2 to the 5 choices, 2 choices for each of the remaining 5 elements. Okay, now, what about 3, 9? This is just like 2, 4. 2 to the 8 minus 2 equals 2 to the 6. Because there's 6 elements left and they each have 2 choices. Okay, so what's our total so far? Well, 2 to the 6 is 2 times 2 to the 5. So we can rewrite this. So our total is 5 times 2 to the 5. 2 plus 2 plus 1. And 5 times 2 to the 5 is just 5 times 32, 160. But we're not done yet, because we have to subtract the possibilities where 2 of them are true by PIE. Because we're overcounting the possibilities where, let's say, our subset contains both 2, 4 and 2, 3, 6. We're overcounting that, so we've got to subtract it to account for that. Okay, so now let's look at how many subsets contain 2, 4 and 2, 3, 6. For a subset to contain 2, 4 and 2, 3, 6, it has to contain 2, 3, 4, 6. 2, 3, 4, 6. Because something that contains all 4 of these elements will contain both 2, 4 and 2, 3, 6 as part of their set. So now how many subsets with 2, 3, 4, 6? Well, we've just done it. 8 elements, right? 8 elements, 4 are fixed, have to be in the subset. 4 have 2 choices, 2 to the 4. And we can just keep going like this. Now, what if the subset contains 2, 4 and 3, 9? 2, 4, 3, 9. Again, 4 elements remaining, 2 to the 4. And also keep in mind that we're not worrying about duplicates here. Because if a subset contains 2, then it contains 2 as part of both sets. There's no 2 2s or anything like that. 1 2 is enough for it to include both of the subsets. Include both 2, 3, 6 and 2, 4. Now what if a subset contains 2, 3, 6 and 3, 9? It has to contain the elements 2, 3, 6, and 9. And 3, even though it's part of both subsets, having 1, 3 is enough to include the 3's as part of both subsets. And there's just 2 to the 4 ways again. 2 to the 8 minus 4. This right here is a total of 2 to the 4 times 3, which is 16 times 3, 48. Okay. Next. So next, now all we have to do is look at the case where all 3 of them are true. Well, for our subset to include all 3 of these things, 2, 4, 2, 3, 6, and 3, 9, it has to contain the elements 2, 4. The 2 is already there, so then an additional 3, 6. The 3 is already there, so an additional 9. So the number of subsets with these elements, well, there's 8 total elements. There's 5 elements here. 3 elements left, 2 cubed. Okay, so now what do we do here with these numbers that we have? Remember how pi works. When we're counting the number of subsets, we add the number of values that have at least one of the subsets. So that in that case, our total was 160. We subtract the values where 2 of them are true, and then we add back the values where all 3 of them are true, like we saw in our Venn diagram I explained earlier. And this is 120. But careful here. Remember, we're doing complementary counting. So we have a total of 2 to the 8 subsets, right? 8 elements, so 2 to the 8 equals 256. And this is the total subsets. And the subsets, 120, is the number of subsets with at least one product. So the number of subsets that are product free are 256 minus 120, which is 136, the final answer. Okay, next we're moving on to stars and bars. So stars and bars is a very clever bijection, which is very useful for simplifying problems, and it's a very special kind of technique that is very useful in many types of competition math problems. But if you're interested in that, you'll have to check out the next video over here.